All right, well, welcome everybody. Welcome back to the Physics Department Speaker Series. I'm Professor Steven Sekula. I'm the chair of the Department of Physics, and it's my pleasure to welcome everybody to this hybrid event. I think we're all looking forward to this getting back to actual normal, where we no longer need Zoom, but we do have a bunch of participants connected, and I want to talk a little bit about how we're going to manage this today. So for the people in the room, if you want to ask a question, it's simple. You can just raise your hand. Tom, you can call on them if you see them. But to help our friends connected online, I have a microphone. So just give me 10 seconds to run to wherever you are in the room so you can ask your question and it can be heard online. For the folks online, to avoid stray ambient noise from people randomly unmuting their microphones, we don't let anybody just unmute. But if you have a question, just type the word question or comment or something like that in the chat window. I'll be monitoring that from the laptop, and then I'll go ahead and let Tom know, and we'll get you called on. You can also type your question in the chat window, and I can ask it for you if it's clear enough to me. Okay? So before we get started today, I wanted to take the opportunity while we have people sort of connected in person and remotely to introduce one of our newest postdoctoral researchers, Xijing Zhang, who you can just come on down here into the camera view. So Xijing is joining us as of, she arrived just a couple of weeks ago, and she's joining the SMU Atlas group. She received her PhD recently completed, and it was jointly conducted between IHEP in Beijing and IN2P3 in France, in Lyon. And her thesis was conducted on the CMS experiment. So she has two culture shocks, one coming to the United States and moving here and relocating to Dallas and going from the high functioning collaboration to Atlas. So welcome, Xijing. And she looks forward to making significant contributions to the Atlas physics program in the years ahead. So let's give a round of applause to Xijing. So thank you. All right, so without further ado, I'm going to go ahead and introduce our speaker today. And I forgot to ask you this beforehand, so I'm going to hack it right here at the beginning. Tom Runcevski?
Yeah, that's correct.
Yes, okay. So Professor Tom Runcevski is going to be our speaker today, and he's going to talk to us about Titan in a jar. Now, he was born in Macedonia, where he finished his undergraduate studies in chemistry in 2011, and he earned his PhD at the Max Planck Institute for Solid State Research in Stuttgart, Germany, with Professor Robert E. Dinneweyer. His graduate work was on structural characterization of materials with diffraction and spectroscopic methods, with a focus on structure, solution, and refinement of polycrystalline materials. He graduated in 2014 with honors and was awarded the Otto Hahn Medal of the Max Planck Society. And after a one-year postdoctoral stay at the Max Planck Institute, he joined UC Berkeley and the Lawrence Berkeley National Laboratory in 2015 as a postdoctoral researcher with Professor Jeffrey R. Long, working on characterization of porous materials. In 2018, he started his own independent career at Southern Methodist University as an assistant professor of chemistry. Let's welcome him today to give our inaugural colloquium.
Thank you. Thank you very much for the introduction. And it's really nice to present in a different department, but the same school. So we can finally meet officially. Before I start the presentation, I have to say that what I'm going to present today is basically 1/3 of what our group is doing. Today, I'm going to talk about Titan in the jar, a little bit poetic title, but I promise there is not that much poetry in the talk. Besides of that, we do work also in the field of material science, particularly sports supplements. So if someone wants to go in bodybuilding, that's something that we do as well. And recently, we started working with antibiotic glasses. And if someone wants to make antibiotic glasses, that is another venue of research of ours, quite recent. But today, I will present what we've done on Titan, Saturn's moon, which I think is quite suitable. Physics, chemistry, and planetary research, they are intertwined. So we work towards the same goal. And I think there is a lot of overlap between the research that goes on Titan from the side of chemistry and from the side of physics. Okay, so Titan. When I say Titan, just to make it clear, I'm talking about Titan Saturn's moon. Titan Saturn's moon is an extremely interesting place. And we know a lot about it thanks to the Cassini Huygens mission that concluded just a couple of years ago. So Cassini-Huygens was a huge mission that explored Saturn and its moon, and there's just some basic facts about it. The Huygens mission landed on Titan and collected a lot of data. That's how we know about this moon. This moon is so interesting that NASA decided to send another mission to Titan in just a couple of years, which is called the Dragonfly, and this is the Dragonfly Rover. What is a little bit different in this mission compared to others is that the Dragonfly Rover will go on Titan. It will stay for a couple of months. So it will not just fly by, it will stay, and it will fly from the desert into the lakes and then to the crater. So it will explore the moon quite a lot. It is expected to touch down in just a couple of decades, so in our lifetime. So if you ask me, now is the time to do research on Titan, because Dragonfly will arrive there in a couple of decades, the moment when I plan to get retired. But between now and my retirement, I would like to make some contribution with our group in helping this mission, and in general, helping to understand how does Titan look like. Okay, so before I start presenting our results and findings, why Titan? And for those of you who are not that familiar with the moon, what is so interesting about that moon? Well, Titan is the only other place in our solar system that has dense atmosphere, and it has also liquid on the surface. There's no such a place in our solar system that we know of. The atmosphere is made of predominantly nitrogen and methane. And then we have the lakes of Titan, which are made of ethane, methane, and propane. There is a lot of going on. In this picture, which I took from NASA, it actually shows quite overwhelmingly what is going on in Titan. I will try to put this very simply with the most important things that are going on. So the first thing that happens here in the upper atmosphere is we have a lot of chemistry fueled by the magnetosphere of Saturn and of course the sun. We have a lot of organic reactions that take place. Nitrogen and methane react. As they react, they produce ethane, methane, and all of these other chemicals that you see. Everything that is being produced is carried by methane. Methane on Titan plays the same role as water on Earth. That is another parallel. So basically, the same cycle, hydrological cycle that we see on Earth, we can see on Titan. However, now we have methane. We have methane that evaporates from the lakes to the atmosphere in the cycles. As it cycles, it is carrying on all of these chemicals to the surface. Also, these chemicals would concentrate in the haze. That's how we have that Titanian haze. It is quite interesting to notice that we have rain of methane. That must be very fun to watch. And not only that we have rains, but there are evidences that we have storms of methane. That's something that is quite interesting to imagine. Just imagine a storm of methane and a hurricane of methane. Anyway, so that hurricane and storm would go down and will touch the ground. As it touches the ground, all of these chemicals will either touch a solid or they will get dissolved in the lakes. Interestingly, only nitrogen, methane, ethane, and propane would be liquid or gas on Titan. Everything else would be solid. So all of these organic molecules that we see here are solids. By definition, if something is naturally produced and solid, that's a mineral. So if we say that benzene for all of us or acetonitrile, they're just simply chemicals that we have in every laboratory, that's for us. That's from our point of view. But on Titan, they are minerals. And that's what we call them, minerals on Titan. If you want to learn a little bit more about it, we recently published an accounts of chemical research that summarizes pretty much the recent results from our lab and the lab in NASA, working on this prospective minerals on Titan. Okay, so why do we as chemists are in the right place to study Titan? As you can see here, the moon, which was one of the first places of humankind to visit, and next Mars, they both and many other comets are composed of common surface minerals, inorganics, silicates, magmatic rocks, and so on. But Titan is completely different. Titan has an organic surface. It has organic surface minerals. And that's the reason why now is the time for a physical chemist to shine. As you can see, the propionation, acetonitrile, benzene, again, simple chemicals for all of us, but minerals from Titan. And we can really help do a lot of, help understand Titan much better if we take a look on the solid state chemistry of all of these materials. What can we learn and why we are interested in exactly these molecules? Well, there are a lot of references, and I just put them there. But let's go step by step and introduce some of the possible areas in which we can make contributions. First of all, detection of minerals on Titan. Cassini collected a lot of data. The interpretation of that data is extremely challenging, and it makes sense. The data is remotely collected. The haze is very dense, so everything that all the probes that touch Titan's ground and collect the data would be really difficult to be analyzed. Only benzene so far has been unambiguously determined as a mineral on Titan. Acetonitrile, for example, is only tentatively determined, and it is known that it exists on Titan, but it has not been detected on the surface. Now, one hypothesis why, and first of all, when I say it is debated, it's debated in the following way. Cassini collected spectroscopic data, and the way how you analyze spectroscopic data is here matching with standards collected on Earth. When you match the peaks of acetonitrile, there is a small misshift, and that small misshift, it's enough to say, okay, we believe that there is acetonitrile, but there is a misshift, so you cannot be 100% sure that it's acetonitrile. So how can we help? Acetonitrile as solid has been compared to whatever data has been collected by Cassini. But who says that acetonitrile will be a molecular solid on Titan? We know it will be solid, but we do not have any proof that it's going to be a molecular crystal. You're a physicist, so just a crash course in solid state chemistry. Molecules can exist as molecular solids, but it can also exist as hydrates, in which we have crystallization with water molecules. They can form clatrates, in which we have crystallization within the framework of ice, and they can form co-crystals. Co-crystals are basically crystals that are composed of two different organic molecules. So who says that if we have acetonitrile in the atmosphere and touches down the lakes, it will crystallize as a molecular solid, especially that we know that we also have benzene. Now, if acetonitrile and benzene combine, and if they form a co-crystal, that co-crystal will have unique spectral signature, which will be different than the spectra of benzene and acetonitrile. The differences will be subtle. So it will be small blue or red shift of the peaks, enough to jeopardize the identification of the mineral, and enough to put some doubts. So that's one of the reasons why we can really work and help identify minerals on Titan. Very similar, propionitrile. Propionitrile has been really debated, not only on the surface, but also on the haze. Acetonitrile has been identified. Propionitrile has not been identified even in the haze. The similar logic and similar story might be told for, here's propionitrile, might be told for propionitrile. This might be the reason why we have not identified. And another reason which really inspired us to go and look in combinations is all of the proposed synthetic routes in these papers for the synthesis of acetonitrile and propionitrile. If you follow the synthetic routes and if you follow the equilibrium, you will see that the energy barrier between the synthesis of acetonitrile and the synthesis of propionitrile are very near, and the energy barriers are very shallow, and the synthetic routes are there. So our logic is, if you have acetonitrile in the system, you probably have propionitrile and vice versa. That being said, it makes more sense to study them together in a mixture than studying them separately. For a lot of people, if you study something separately and in the mixture, it doesn't make that much of a difference, but for solid state chemistry, it makes a huge difference. And that will be the second part of my talk. So the first part will be acetonitrile and benzene and what we can learn about that combination. And the second part of the talk would be the composition of a mixture and how a mixture can change the properties of the system. Okay, let's start. First, we start with these two molecules. We know that they exist on Titan. We have identified them in the atmosphere, and they will touch down on Titan. They will get dissolved in the lakes. The solubility constant of both of them in ethane are very low, so they will crystallize. So let's see how they will crystallize and how they will form minerals. Just a reminder, this is a phase diagram of a mineral on Earth. Earth is predominantly made of minerals like this. So we have calcium, silicon, and aluminum, and we have all the oxides. All of these are minerals on Earth, and this is how the phase diagram looks like. Incredibly complicated. Our goal is to do similar phase diagrams, but for acetonitrile and benzene. Again, that makes sense because what is on Earth silicon, you can imagine that to be on Titan benzene or aluminum acetonitrile. Of course, the correlation doesn't go that simple, but you get the point, what we want to achieve. Okay, how do we make this phase diagram? There are two ways. There are actually many ways. First of all, we can look at crystallization, but that's not a good idea because crystallization can be a stochastic event that may be determined by even impurity. If you have a seed of crystal, you will have crystallization. So it's not thermodynamically driven. On the other side, melting is. Melting is a very thermodynamical event. That's the reason why we decided to look at the melting peaks, on the endothermic peaks of mixtures of acetonitrile and benzene. What we have here, we have prepared a couple of mixtures, and Christina did this here in our lab. We have mixtures starting from pure benzene till we go up to pure acetonitrile and all of those combinations. As you can see here, we have different endothermic peak maxima, minima in this case, that are shifting. And as they are shifting, they are outlining the phase diagram of acetonitrile and benzene. Looking at this peak minima, we can plot the phase diagram. And this is the solid liquid phase diagram of acetonitrile and benzene that is being created in our lab. And here below, of course, would be the region that we as chemists would be interested for Titan. Okay, let's take a look now on the phase diagram and what we can learn by the phase diagram. Well, we can learn a lot. We can, for example, learn that here we have a fusion line. Here that we have one solid and one liquid phase. This is this part. This is a fusion line. Then we have here probably two solid phases. Here one solid, one liquid. Here also two solids. But as we can see, we don't really see what is inside. And this does give us a lot of information, but it's not enough. And it's just lines. We just know where the phase transformation will happen, but we have no idea what is going on inside. Of course, here we have one liquid phase that is easy, but this place of the phase diagram is really complicated. If we really want to study what is going on in the phase diagram, we need some structural evidence and some structural probe. So the way to go is we're taking this isoplates. In this isoplates, we need to collect data as a function of temperature, cover all of the phase regions with some spectroscopic or diffraction technique. There are many different techniques that we can work on. Arguably, the best one is X-ray powder diffraction. The reason why it's the best one, X-ray as a probe is quite fast, so you can be collecting data for a couple of seconds if you use synchrotron radiation. On the other side, powder, it's easier because you don't have the need to grow single crystals, large single crystals. The sample preparation is very easy, and the handling of the samples is also very easy. We did exactly that at the synchrotron at Argonne National Lab. We can do this in the lab here at SMU. We do have the equipment. However, one set of data will take us 24 hours. At Argonne, one set of data takes us a couple of seconds. So basically, we can make the same. We can collect all of this data at SMU, but the data collection will be done by the time that I will need to submit my tenure track package. And that's not going to work. That's why we went to Argonne and we collected data within just a couple of hours, and we covered all of the phase regions. Okay, so here I will present just one set of those data and what we can learn about them. So we are going here, and we're cooling down. As we are cooling down, we are touching through all of these phase regions, and we're collecting data. This is how the data looks like. So here is the temperature scale. And here is a 2 theta angle. A 2 theta angle, as you know, is the signal from the X-rays, and these are the bands. If you take just visually a look on what kind of this two-dimensional plots are showing us, we'll see here that we have extra peaks because we have here two solid phases, and here we have changes which corresponds to this place here. And here we have no peaks because this is liquid, and liquids do not give coherent scattering of X-rays. The next thing that we do is analyzing the data on each of these regions. This data analysis is relatively difficult. For those of you who are experimental physicists, you might know solving crystal structures from single crystals is very straightforward because you have single crystal, which is a three-dimensional object, and you're collecting data in a sphere, which is also a three-dimensional set of data. Because of that, you have a straightforward mathematical problem, three-dimensional data, and you have three-dimensional solution. On the other side, with powder patterns, as you can see, we have one-dimensional data that spans on the two theta axis. So we have one-dimensional data, but we have still three-dimensional problem to solve. That being said, this is an extremely challenging thing to do, and there are only a handful of research groups that are doing this type of analysis. Not only that we are able to do this analysis, but also we are able to do phase mixtures and simultaneously determine the crystal structures of a couple of phases in the pattern. And by doing so, we can really see what is going on in each of these regions. As I said, here I present just one isoplet, but that can be done in each of these regions, and we can cover the whole part of the phase diagram. By doing so, we can solve the structure, and this is how the structure looks like. So in this area, I'm just showing one phase transformation. As we can see, this is pure benzene. In this region, we have solid benzene. Acetonitrile is in liquid form, and that's why we don't see it. Here, acetonitrile below this phase line is reacting with solid benzene, which is called the peritectic reaction or peritectic phase transition, and is penetrating into the crystal structure and is forming a co-crystal. In this case, we have two phases. One is the unreacted benzene, and the other one would be the co-crystal that we assume that we will find. By doing so, not only that we are able to look at the phase lines and see, okay, we have a phase line and we have different phase regions, but with combining these different techniques, we are able to really see what is going on in each of these phase regions. So as we can see here, in this region, we have solid benzene, and this is the phase stability region of benzene under these conditions. At this place, this part of the phase diagram, not only that we have benzene, but we have the 1 to 3 acetonitrile benzene co-crystal. In this region here, we have beta acetonitrile, here we have alpha acetonitrile, and of course, this is just liquid. So these are the solids of acetonitrile and benzene. The most notable one for Titan would be the fact that acetonitrile and benzene would form this type of co-crystal. The next step in our research, which we have not done, but it's definitely the natural progression, would be to study the spectral signatures, because this co-crystal might have that misshift and explain the identification of acetonitrile and solved quite long-standing problem in the structure of Titan. But there are other ways of how we can use this co-crystal to study Titan. So these are the lakes of Titan, and one extremely interesting thing about it is the cycling. The lakes are known to evaporate and then precipitate and form lakes again. So you can learn a lot about the history of Titan if you know at which parts there was a lake and at which part there wasn't a lake. So the existence of this co-crystal may serve as an indicator for past or future presence of ethane because of the following. We realize that when we have contact with ethane, the structure of this co-crystal is changing. We don't yet know because these powder patterns are so complicated to be analyzed, and we are working in that direction. But the patterns are changing. So as you can see here, we have peak splitting upon contact with ethane. Even though that we don't know now the structure of this co-crystal, this is still relevant as an indicator for past presence of ethane. For example, let's say that if tomorrow we identify this peak splitting on the surface of Titan, which is dry, that may indicate that sometime in the past there was ethane and there was a lake there. And I do think that it is quite useful for the future analysis on Titan. There is another way how we can look at this data and how they can be meaningful in the genesis of Titan. That is the ethane ocean problem. So and that's the name of the problem, the ethane ocean problem. Based on the based on simple calculations of how much ethane is being constantly produced in the atmosphere of Titan, there should be an ocean of ethane on Titan. When Cassini flew by, it did not see any ocean. And ocean is not something you can easily miss. It's huge, it's ocean. You should see it, but Cassini did not. One possible answer why there is no ocean is maybe sequestrating of ethane in a form of co-crystal. So in this case, if ethane really penetrates this co-crystal, then instead of seeing an ocean or liquid of ethane, it may be sequestrated similar as it, for example, ice on Earth create a solid, and that's the reason why we would not see it on Titan. And there are other ways of how we can use this knowledge to learn a little bit more about Titan. We also feature that on the cover of ChemCom. This is Dragonfly. It will not be this beautiful. It is just an artistic representation of how we would look at it. Okay, so that was the first part of the presentation, and now we'll jump on the second one, acetonitrile and benzene, and we'll focus on this part here, on the part that on the logic that if we have acetonitrile, we'll probably have propionation in the system, and vice versa. So we'll have both of them together. So far, they have been studied separate one from another, but as you can see, a lot of things are changing when they're together. Okay, let's start step by step. The first one, the acetonitrile. What we know about it is that we have two polymers, the high temperature polymorph and the low temperature polymorph. And there is a phase transition between them. So here we have liquid crystallization in the high temperature polymorph. This is the place where the high temperature polymorph is stable, and then polymorphic transformation to the low temperature. Propionation has the same. With the difference is that the crystal structures of propionation were not solved. And that is quite surprising. This is propionation. It's only a couple of atoms. The fact that we didn't know the crystal structure of propionation in the 21st century is shameful. We know so many complicated things, but not to know the crystal structure of one of the most basic molecules is, again, shameful. For us as chemists, for you as a physicist, it's a little bit better. The crystal structure was reported on the low temperature polymorph in 2020 by the time that we actually have solved it. We were scooped. That was one of the worst days in my life. However, it happens. The reason why we haven't published, and we still haven't published, is because this article here presented just the crystal structure. As I will present, we collected a lot of data because we want to present a comprehensive overall study on propionitrile and acetonitrile, followed with diffraction, spectroscopy, total scattering, neutron analysis, and so on. So we waited, and that paper should show up anytime soon. We also solved the crystal structure, the high temperature, two chemicals, but in general, for simple chemicals like this, just to figure it out the phase diagrams. Very fundamental, very simple science. But it does give us a lot of information and a lot of interesting data on the behavior, the phase behavior between these two chemicals. So we have the phase diagram, what we can do with it, and how we can correlate it to Titan. Well, there are a couple of things. Let's start with one of them. So here, what I present is, as you can see, this familiar picture that I showed. So propionitrile and acetonitrile would be synthesized somewhere here, and then they will just go down. And here, what we have is a temperature plot. And as you can see in the mesosphere, up in the stratosphere, we have relatively high temperatures. So here, those temperatures start going down. As they're going down, from around here to around here, we have the Haze layer. So the Haze layer, this is the Haze layer, forms because the temperature goes down, these molecules condense, which makes sense. As they condense, they form aerosols. As they form aerosols, we have that characteristic haze. And this is that Haze layer. And then the temperature goes actually a little bit up, and it touches down. So let's take a look. Let's take a look in this part. We have a drop of temperature, which is quite significant. And this is the phase diagram. Why and how are these two related, and how this can help Titan, understanding the structure of Titan? Well, take a look. Here we have around 60 Kelvin difference from the top part of the layer to the bottom part of the layer. And that corresponds to 50 kilometers in altitude. Look at the phase diagram. If you take a look only on acetonitrile, which is not mixed with propionitrile, it will crystallize around here. But look, if you mix it with acetonitrile, the lowest point of crystallization will be the eutectic point. And that eutectic point it's around 60 Kelvin lower than the crystallization of pure acetonitrile. That means that if we have it mixed, this difference of 60 Kelvin may translate to 50 kilometers difference in altitude. This is important because, as I said, for example, propionitrile is not being identified in the haze. We may be looking at different altitude. We might expect crystals of this nitriles at certain altitude, but because they're mixed and they're not alone in phase pure, we may encounter them in a different altitude. And this is just a mixture of two, but as you can imagine, Titan is a mixture on a planetary scale. So we definitely need to work a little bit more in the direction of figuring out what is going on. As I said, we can get all of this information just by looking at the boundaries, but very similar to the case of propionitrile and acetonitrile, we really don't know what is going on here. And the only way how we can learn is doing diffraction and solving all of those crystal structures. And this is exactly what we did. So we first followed pure acetonitrile, then pure propionitrile, and then we went ahead to go and cover the rest of the phase diagram. And as I said, a lot of these phases are unknown, so let's talk about it. Let's first talk about pure acetonitrile. These two phases have been known for a couple of, for decades now. What we notice, and it's quite interesting, is that when we cool down the system, we have quenching of the monoclinic high temperature phase. So what happens is we would expect when we cool down to have first the high temperature form, which is monoclinic, and then phase transformation into the orthorhombic low temperature form. We do not see that. And the reason why we do not see that, it is strange, but not that strange. It's just kinetically trapped, and we have the low temperature form being stabilized at the high temperature form being stabilized at low temperatures. As we're heating up, we are giving the system a little bit of nudge, so it can really go back and get this phase transformation to the low temperature form, then another phase transformation to the high temperature form. So there is a little bit messy here, and then finally we have melting. What we'll learn from this experiment is that, sure, we have the high temperature and the low temperature form, but there can be switch between them based on whether the crystallization is under more kinetic or thermodynamic control. How is this relatable and why is this important for Titan? Well, on one side, we can say that if acetonitrile cools down and rains down quite fast, we can have this quenching. Then the next question would be, will the high temperature form stay high temperature or monoclinic throughout time? There are two arguments there. On one side, it's quite cold, so it's very difficult to have a phase transformation if you don't have that energy input. Think about glass. Glass should not exist because it's metastable form. It should crystallize. Yet glass doesn't crystallize. We all use glass. Similar thing can happen with acetonitrile. On the other side, we're talking about perpetuity. So eventually there might be that phase transformation. That is quite interesting argument to be made. And future experiments are needed to figure out what is going on. It is also interesting to follow why this phase transformation is trapped and why it's kinetically controlled if we take a look on the structure of acetonitrile in liquid. The structure in liquid, which was solved by PDFs, it is very similar in the high temperature form. Here, as you can see, we have that head to tail type of orientation, head to tail. So in order for the high temperature form to go to the low temperature, we need to have switch of this head to tail to head transformation that requires a little bit of energy. That's the reason why we have kinetic control of the high temperature form. We also follow this type of experiments with our lab, and in our lab, what we do is we take total scattering data, and by doing the PDF analysis, pair distribution function, we can figure it out the liquid structure of the system as well. Okay, propionation now. Propionitrile behaves a little bit more logically under our conditions. When we are cooling down, we have the high temperature phase crystallizing as expected. Then we have the phase transformation to the low temperature form. And once it's heating up, we have again the high temperature form. This one was solved and we were scooped, but these two are not solved. Were not solved. We solved them and we are looking forward to publishing all of this data together. As I said, things are working out a little bit more logically here. It is interesting to see that acetonitrile has this quenching, propionitrile doesn't. That just shows us how complicated this small molecules can be. And it's the same with propionitrile and acetonitrile. We have also that head-to-tail type of structure in liquid, which is very similar to the one that we have in the high temperature polymorph. But as you can see, similar type of structure we have in the low temperature form as well. And that might be the reason why there is not that much of quenching, meaning it is very easy to go from this polymorph to this one, as opposed in acetonitrile, in which flipping of whole layers should occur. This is how the patterns look like. This we also notice quite interesting structural effects in these two polymers, but we don't really have time to talk about it. But we will move to a mixture. When we have a mixture, we have really complicated behavior. First of all, if you remember, I said that acetonitrile is getting quenched when it's pure. For some reason, when it's mixed, that quenching doesn't occur. The high temperature form does not even exist. It's directly go to the low temperature form. On the other side, propionitrile is now quenched. Now we have the monoclinic form of propionitrile being quenched and the orthorhombic form of acetonitrile. When we are heating up the system, we have again interplay of the phases. Long story short, this is extremely complicated, and at first it does not make sense. But if you think about it, all of these phases that exist, the energy minima are very related. So it's very easy to go from one structure to another. It's very easy to have quenching or not to have quenching. If you have a mixture with the sole existence of one phase as a crystal, it can nucleate another phase on top of it, and by that you can have a completely different sequence of polymers. The take-home message is, if we want to guess what kind of structures we will have on Titan when we have pure or mixed acetonitrile and propionitrile, it is an utter mess. And we can make assumptions what would be the most stable one. We can say, okay, the acetonitrile in the orthorhombic form might be the most stable one because that one has been quenched and it's stable, and in perpetuity should not transform to anything else because it's a thermodynamically stable form. But what would be the second most likely structure on Titan? We don't know yet, and that is important because, as I said, we have to compare the spectroscopic data that we collected on Titan with laboratory standards. What are we comparing with? This one, or this one? And it's quite complicated, and it's important in order to really see what is going on Titan. And before I conclude, let's go and talk about basically the solid state chemistry on these minerals, on these materials, and what we can learn from them. I decided to present four different things that we focused on. We can learn something about them. And first, we will focus on thermal expansion and the potential influence of particle size on Titan. This is the thermal expansion of acetonitrile and propionitrile, whether they're mixed or whether they're alone. What is thermal expansion? Well, you're physicists. You probably cover that quite from a different aspect that we do. It's basically the response to the solid on temperature. Normally, when you heat something because of vibrations, things are expanding. It's hence thermal expansion. But if we take a look, we have quite interesting behavior of acetonitrile and propionitrile, and this might be a little bit of a better representation on the thermal expansion. So first thing that you can notice is a very pronounced anisotropy of thermal expansion, which is not very common. Commonly, solids would expand in every direction pretty isothermally. But in this case, because of how the crystal structure look like, they expand completely anisotropic. Moreover, propionitrile, the metastable form, high temperature form, the monoclinic, is featuring also negative thermal expansion. It's uniaxial. It's uniaxial negative thermal expansion is unusual, yet it's understandable from a structural point. But it's quite interesting. And now why is this interesting for Titan? For us as chemists, it's great because thermal expansion is something we can use in functional elements, and it's very important to understand the structure of solids and so on. But why should we care in regards to Titan? Well, here, from the Haze layer, when we may have these molecules, these crystals form, from the Haze layer, they would need to descend and touch ground. As they are descending and touching ground, as you can see here, the temperature is actually increasing, and the temperature here is decreasing. So as the temperature is increasing and decreasing, also on the surface of Titan, you have cycling, and during that cycling, you have differences in temperature. The differences in temperature would cause crystals to expand and shrink. If this shrinking and expansion is anisotropic, can easily lead to fracturing of the crystals. If you have fracturing of the crystals, the spectroscopic data that you're collecting will be influenced by that fracturing, which is completely normal because we have the scattering will be different from fractured surface compared to the nicely polished surface, and that might explain why we see Titan the way we see it, be very fractured. Again, further theoretical analysis in this case are necessary to really understand how this fracturing works. Okay, next, the macroscopic structure and how this can be potentially related to life. There is a paper which is quite interesting, it's quite recent, can polarity inverted membranes self-assemble in Titan? So polar structures are important for the origins of life and how these minerals can really help in this direction. Well, I will not go in detail, but we also saw the structure from single crystal, and having combined powder and single crystal together and analyzing the preferred orientation, we can really learn how the crystal will look macroscopically and which facets would be exposed. And this is quite interesting and quite important because, as you can see here, these are the preferred orientation faces of propionation. And some of these faces are polar. This polarity can actually help and have influence in potential origins of life type of scenario. If we have a polar surface that can help grow and self-assemble other molecules on top of that surface. That's one of the theories how life on Earth started. Of course, we don't work in that direction. I'm not saying that we're working in origins of life type of research, but what I'm saying is that this, figuring out what is the hydrological makeup of Titan might help that research as well. Next, vibrational structure. As I said, I mentioned it a couple of times why vibrational structure is important, and we do research in that direction too. What we work is we collected the Raman spectra. This spectra were collected at Argonne National Lab with Raman probe that it's not. There was just the remote sensing, so the quality of the spectra is not very good. We're not able really to tell the difference between different polymorphs and between the co-crystal and so on, because our data was not, very high quality. However, thanks to the NSF and the new MRI funded project at SMU together with the Lyle School, we got a Raman spectrometer, which will arrive and be installed at SMU in just a couple of months. So I'm really looking forward to redoing this experiments and figuring out how high resolution Raman data would look like. Even though we have the low resolution data, we can still analyze. We can still learn a lot about the spectrum. This is quite interesting. So you can see this is the calculated spectrum of propionation in gas, but the experimental spectrum is quite rich, and it doesn't really explain all of the bands. The reason why is, even though these molecules are so simple, not only that you have the fundamental vibrations, but you also have first overtones, and you also have combination modes. And together with Elfian, with mainframe here, we were able to really explain by DFT how all of this fundamental first overtone and combinations work. This is an excellent exercise for those of you who like a group theory to really calculate from scratch how these vibrations will go. I did my master's in Macedonian there most of my professors were very much into that, into calculating the group theory, what kind of shifting there will be, quite simple yet powerful mathematical concepts. So feel free. But of course, that kind of analysis will not give you this beautiful gifts of how this vibration happened. And if you have DFT, you can really learn a little bit more about how really this vibration happened. You can visualize them. It's not just the pleasure of solving a mathematical equation and matrices, but also visualizing them and see that they're real. They're not imaginary. I'm also very excited to present this data that were collected just 2 days ago. And this data were collected at Oak Ridge National Lab. So this is vibrational neutron spectroscopy. Now, this is something different. The Raman, as you know, the Raman spectroscopy uses photons to excite and to collect the spectra. Vibrational neutron spectroscopy does absolutely the same, except doesn't use photons, but neutrons. And that is quite exciting. The reason why, when we have interactions between photons and the electron cloud, we have a lot of problems in the data analysis. But if we have interactions between neutrons and the nucleus, this should be very straightforward for calculations. Having that in mind, having that ease of calculating, we're able to really explain the system much better than using Raman spectroscopy. It is a beautiful technique. The problem with this technique is it can be done only at 2-3 places in the world. So it's not very common as you can just go in the next door and then collect data. But I'm very happy to have the collaboration with Oak Ridge. They're now very excited, so I'm looking forward to collecting more and more data and establishing a really solid collaboration with them. Okay, and finally, I will go and talk about dynamics. When people think about crystals, they think about they're static and they don't move. I think about rocks, but that's not true. We think of crystals as solids just because it works in our favor, because then we can neglect the dynamic structure. But should we do that? No, we should not. We should also look at dynamics. How should we do that? So this is the quasi-elastic neutron scattering spectra. Quants. As you can see here, we are cooling down. Here we have quite much of a mean standard deviation of the hydrogens, being very stochastic and being random because this is liquid, which makes sense. But then if everything is static and there is no movement, once we have crystallization here, we should have drop. Fine, we have that drop, but that drop should go to 0. But it doesn't. From here, it takes up to 50 Kelvin, and of course here is 0 because here we measure data down to 5 Kelvin, and 5 Kelvin nothing moves. But above 50 Kelvin, especially above 100 Kelvin, we have a lot of movement. So that means that not only that we have movement, but that movement is significant. We're able to analyze the data. That we have the data. This is the partial fit with and without the Lorentzian function. The Lorentzian function can give us information about the movement, and it can really help us calculate the jumping and what kind of dynamics we have if we collect data at a couple of plots. By doing so, we realize that in Propionation, this metal group is actually jumping, and this is perpetually rotating, and that threefold jump happens at 1800 picoseconds timescale in perpetuity under conditions of Titan. And this is quite important. Of course, for us, for purposes on Earth, might be insignificant. But when we're talking about Titan, this might be significant. When we're talking about potential life on Titan, this might be significant because, again, one of the reasons why NASA sends the Dragonfly is the origins of life story, but no one expects on Titan to find Starbucks and life like we have. The life on Titan would be different, and this type of movement might be energetically enough to help that kind of story about the origins of life. Okay, so I will conclude now so we can have some time for questions. For acetonitrile and benzene, we show that with DSC and peak 3D combined with colorimetry and diffraction, we can really get the phase diagrams, and we can correlate that with Titan, learn a little bit how the simple yet interesting studies can teach us something about the moon. The same goes with acetonitrile and propionation. But actually, if I really have one concluding sentence, then I will say that the research in Titan has just started. These are only 3 molecules that we talked about. There are 30 that are detected. Nothing is known for most of them, and those are those that have been detected. Titan is a moon. Titan is not a small little jar, but it's a laboratory on a planetary scale. And now is the time to really analyze and make these systems more and more complicated. And finally, acknowledgement. We have this type of research cannot be done without the help of large-scale facilities because of the experimental techniques. So we have the help from NIST, Argonne, Oak Ridge, for neutron diffraction and X-ray diffraction and total scattering and vibrational spectroscopy. At NYU, we did the single crystal X-ray diffraction analysis and also mainframe for the theoretical calculations. And finally, to acknowledge research group and funding from the World Foundation and from NASA. And thank you very much for your attention and for the invitation again.
Thank you.